Le record est lancé.
Are we starting? Ah non.
We should start. Per attivo lo stage.
Yes.
Tu veux que je laisse là ou on s'en fout?
Oui, je sais. J'attends Riccardo.
Tout marche.
Oui, on a eu quelques soucis, mais je pense que maintenant tout marche. Okay, so welcome back to the third lecture. Today, just for as a reminder, if you want to come with us to have lunch together, just come to me and I will give you a ticket if you come from outside. And okay, that's it. Thank you.
Thank you. So today I wanted to talk about entropy. Entropy is what I will write it in large letters on the board. The word entropy was coined by Rudolf Clausius in 1865, and this helped clear up some confusion at the time about what the quantity was that was, for example, implicit in Carnot's discussion of the Carnot cycle. Carnot's monograph, by the way, is very interesting to read. There's a nice version with a modern annotation that explains many of the things that were going on at the time, and which I read in my early days of trying to understand statistical mechanics. And so the concept of entropy had been implicit but not really brought out. And Clausius was the first person who really brought it out. And his basic statement was that we could think of, if you think of a system which is exchanging heat with an environment, and it exchanges an amount of heat delta Q, if you divide by the absolute temperature, that's the change in a quantity entropy, which can be thought of as a state function, something that is a monotonic property of the system. All right. And the word entropy, it comes from Latin and means something like intrinsic direction. because, of course, the idea was that entropy would increase in a system left to itself. It's a great coinage, I think one of the most successful ones in all of physics, and so much so that everybody wanted whatever they were talking about to be entropy also. Famously, Claude Shannon in 1948 came up with the concept of information entropy. He didn't originally call it entropy, but there's a story, which we don't know if it's really true or not, that he asked von Neumann what he should call it. And von Neumann said, well, you should call it entropy because nobody knows what entropy is anyway. And it kind of looks like entropy, so call it entropy. And so he did, and all right. But I think it is possible to unify all these different concepts of entropy in a single framework. And so I want to talk about that. And then later today, I will talk about a particular kind of entropy, entanglement entropy, and how that intersects with eigenstate thermalization and some of these other ideas that we've been talking about. Okay. Also, I want to tell you, well, I want to start out telling you something that's quite simple, and which I learned in my first graduate level statistical mechanics class, which at Stanford. I told you the story about how I got into this business because I had been somewhat randomly assigned to teach statistical mechanics when I was a relatively new professor. My class in statistical mechanics was taught by a general relativist, Clifford Will, who randomly got assigned to teach statistical mechanics because there wasn't anybody else to do it at Stanford at that time. And so statistical mechanics is even less relevant to general relativity, to the day-to-day work of a general relativist than it is to a quantum field theorist like I was. But Clifford Will rose to the occasion and taught what I thought was a great course, and I still remember it quite well. And the textbook he used was, even at the time, a rather obscure book. It was Principles of Statistical Mechanics, the Information Theory Approach, by a mathematician named Amnon Katz. Principles. And it's less than 200 pages. It's a little book. And today it's long out of print. I just checked Amazon yesterday. They had one used copy for $500 US, which I don't recommend you spend $500 US on. But the approach that Katz took in this book, which I think is pioneered by Edwin James, is the idea that information entropy should sort of be the central concept of statistical mechanics. And the idea is that a system will want to make its information entropy increase. Now, what was missing in Katz, and I think also James, was really an underlying dynamical explanation of why the entropy wants to increase. There were sort of words about how this was natural and so on, but again, what I've been talking about previously is a quantum dynamical approach, which I think is necessary, and in the classical realm, something like the approach that Khinchin took, we do need some dynamics to supplement this. It's not enough just to declare that we have this concept. Nevertheless, the concept is extremely useful, and I thought that Katz's approach to this is very clear, in my opinion, and as far as I know, is not widely known. So I'm going to tell you about that, and then we'll eventually build up to more and more concepts of entropy that will be useful. Put it in the middle. So what I like about the approach is that it's very basic. So the idea is that if you don't have full knowledge of something, there's some information that's missing. And we would like to quantify the amount of information that's missing. So first we will start in, so this is what we are trying to do. Quantify missing information. So the very simple situation that we start with is we have n boxes, and somebody has put a ball in one of the boxes, and we know that there's exactly one ball in the n boxes, but we don't know which box the ball is in. So we do not know which. So we will declare that there's an amount of missing information I, and of course I should depend on the number of boxes. And now we're going to just try to apply some intuitive ideas to this. So the first is that I of n should increase with n. Right, so if there are more boxes, you don't know which box it's in, there's more information that's missing. And then if there's only one box, the amount of missing information is 0. If there's only one box, you know where it is, you know everything, no information. Okay, and now let me suppose that each box has inside of it m compartments, or sub-boxes. And the ball is in one compartment in one box, and we don't know which box, and we don't know which compartment. So this is where we really make the key assumption, which is that information is additive, or the quantity of information is additive. So what does that mean? Well, suppose I first tell you which box the ball is in. If I tell you which box, I've given you an amount of information I of n. And then I tell you which compartment the ball is in. I've now given you an amount of information I of m. And if we add those two amounts of information, that should be, well, now if I've told you both the box and the compartment, I've told you everything. You now know exactly where the ball is. So there's no missing information. On the other hand, this problem is clearly equivalent to a problem where I don't call these compartments. I just say I have m times n boxes. So if we add the amount of information for the box and the amount of information for the compartment, we get the total information, which should now be I of mn. And again, the key assumption is this plus sign, that this should be an answer. And I sort of already snuck that in by telling you that I of 1 is 0. 0 is the additive null, if you like. Anyway, so this is the key assumption here. Okay. And this, combined with monotonicity, basically tells us that I of n has to be k log n for some arbitrary constant. Positive. And I will take the log to mean natural log. We could, of course, use different bases, which could also be absorbed into what we mean by into changing the value of k. Okay. So now we can already start to recognize a connection with statistical mechanics.
Can I ask a simple question? Is there
Absolutely no other function in log n that satisfies this property, and with monotonicity.
I think so. We can if we say that m and n are not necessarily integers but real numbers, then that's easy to prove. I think it's even true just for integers, because I think the most general thing you could do is use a different base for every prime factor. But then knowing, that 2 to the 10 is close to 3 to the 7 or something will then tell you that the different k's have to be the same. So, in Katz's book, he declares first that we'll define it for rational numbers by putting a minus sign, and then invokes continuity among the rationals. Other questions? Yeah, please interrupt with questions at any time. Okay, so we can make a connection to statistical mechanics, and in particular to Boltzmann. On Boltzmann's tomb in Vienna, there's an equation on the tomb, which is, if the symbol's right, S is equal to k log w. So this is essentially identifying statistical mechanical entropy with this notion of missing information, where k is now Boltzmann's constant. And w, according to Boltzmann, is the number of microstates for a given macrostate, which defines the overall system. Now, Boltzmann, of course, was thinking classically. Quantum mechanics was being born about the same time as Boltzmann was thinking about these things. But okay, and we'll come back later to what this might mean more precisely. But this is we can make the Boltzmann identified entropy as a log of a number of microstates, and here the microstates is sort of which box is the ball in, and our missing information is proportional to the log of microstates defined like that. Okay, but we want to do better than this. I'm gonna set k equals 1 from here on. Okay. So a more refined version of the box problem, and again, I'm continuing to follow Katz's book here. So we'll come back to StatMech. Suppose box I has probability Pi to have the ball in it. All right, so this is a more refined version. Now instead of all the boxes being uniform, we assign a probability. Let's see, I think I'm changing my notation slightly. There will now be little n boxes. And of course, the probabilities have to sum to 1. Okay, but what does it mean to have a probability? So we will say that what it means is that if we do the experiment, now I'm using capital N in a different way, and by experiment I mean somebody has put the ball in a box according to these probabilities, and then we go and look at the boxes and see which one it's in. We do the experiment n times, where n is very large, we will get box I npi times. It's basically a frequentist definition of probability. I'm a card-carrying Bayesian probabilist, but we'll let the frequentists have their day for now. Okay, so that's what we know. That's what it means to know the probabilities in advance. So that's not missing information. This is information we know. But what we don't know is what order we get the results. Okay, so we can ask how many inequivalent orderings are there? And so by inequivalent, I mean, of course, if you get box 7 here and here, if you swap them, that's the same. All right, so the number of, I'll just call it the number of orderings, W is by standard combinatorics I'm calling it W because I'm thinking of this as the number of microstates, the number of possible ways you could order it for a given macrostate, the macrostate meaning how many times we got each result. And so, but now we want to define the missing information per experiment, or per trial, whatever. And so now we'll take the limit as n goes to infinity well, I guess that. Sorry. Writing this. All right, so we just take log W according to our general formula, but now we want to know that's the amount of missing information for n trials, n experiments, and so now we're going to divide by n and take the limit as n goes to infinity, and so this is straightforward using Stirling's formula. Minus signs, right? So we use Stirling's formula on the factorials, and I will spare you the details, but you can easily check. That we get minus sum on pi log pi, which is the Shannon formula for information entropy. All right, so I like this. I looked the other day at the Wikipedia article on Shannon entropy, and it just sort of pulls this out of the hat, said some words. This whole story I've been telling you, I think, is more compelling way to get that. Starting from a basic principle that we will declare that information is an additive quantity, and then we can get to this. And I've never read Shannon's original paper, so maybe that's in there too. But, all right. Now we want to generalize this a little bit further to quantum mechanics. Maybe I'll write it up here for a bit. So I'm sure all of you are familiar with the notion of a density matrix. I don't know why we call it a density matrix. It's not. We often think of it as an operator, but for some reason the phrase density matrix has entered the language. And this is a generalization of a pure quantum state, where we say that the actual quantum state of the system, is one of course we can generalize we can take an infinite limit, but we'll say there's one of n possible orthonormal states So I have a set of orthonormal states, and we think of these as each of these is a quantum state that might be the state of the system. We don't know which, and but we do know that there's a probability p sum I. And this is a probability in the sense that I tell you the probability of the box here. This is not a quantum probability that you get by squaring a quantum amplitude. This is some information. This is some missing information probability. Anyway, then we just declare that the density matrix is that. And you take the trace of rho, that will just end up being the sum of the probabilities, which, again, these probabilities should sum to 1. Yeah.
So, right now you said that this P, these probabilities is a classical probability, and it's like in a sense of the we're missing information. But wouldn't that mean that if we had all the information, then the state would be in a specific, then the system will be in a specific state I?
I'm going to say yes, but I'm slightly worried that you're going to.
Yeah, because it's like in a density matrix can describe a system that is, I don't know, in a thermal state, and that doesn't mean that the system is in a specific. It's not a problem that we're missing information. Is that the system is in a mixture of states.
Yeah, okay. So I don't have a definitive set of words that I want to say about this, so I accept any set of words you or anybody else may want to say about it. The only thing I want to say is that we don't get these probabilities by squaring some quantum amplitude. Right? Okay. Now, whatever you want to say, and I'm thinking I may talk more about these sort of quantum issues on Monday, actually, because I think I may run out of stuff to stay on statistical mechanics. But yeah, so whatever, all right. So I'm not trying to say anything special or provocative here. Whatever understanding you have of what a density matrix is, I'm happy to accept. Okay, and so now, and I think I will now finally switch to a symbol S. We can define what is usually called the von Neumann entropy. And I can't spell entropy, so S, which is minus trace rho log. And if we plug in this rho, this will just reproduce the Shannon formula. But the advantage of thinking of it like this is that this is now invariant under a change of basis, where, or more generally, any unitary transformation on rho. And I just want to mention in passing, I'm not really going to talk about this. A generalization to the Renyi entropies is we have a number alpha . And so instead of taking a logarithm of rho, we raise rho to the power alpha. And the advantage of this is, especially if alpha is an integer, this can be much easier to compute by various methods. And then the von Neumann entropy, the trace rho log rho, is then the limit as alpha goes to 1 of the Renyi entropy. And so one approach to trying to calculate von Neumann entropy in a situation where it's hard to take the logarithm of rho is to calculate it for integer values of alpha and then try to do an analytic continuation and then take the limit after doing the analytic continuation.
Do you take a log of trace?
A log of trace. Log of trace, yeah. So, and again, this part is not so important. It's that you're taking traces of rho to some power, and then you analytically continue to alpha approaching 1.
Suppose we have all of the range entropies for integer numbers and that our states I are also discrete, they're integers. If we have all the range entropies, can we reconstruct the PIs?
I think so, yeah. I think in that case, there's no ambiguity in that case. There's an ambiguity in infinite dimensional Hilbert spaces, and then one has to invoke some analyticity properties, which I think it's a little bit dicey in some cases to invoke those, so people argue about whether this gives the right answer. Okay. So I'm going to go back to the von Neumann entropy, and so if we wanted to calculate the von Neumann entropy, somebody would have to tell us this set of p sub i's for some set of orthonormal states. But often that's not what we know. So yet another version of entropy I call the Jaynes entropy after Edwin Jaynes. I'm not sure, maybe it has some other names also. But certainly Jaynes emphasized in his work this concept. So instead of saying we know this set of PIs, we say that the known quantities are the expectation values of a set of observables, maybe only one, but in principle a set of observables, put an index on there. So in general, the quantum state of the system, we'll say, is some density matrix rho, but we don't know the individual PIs necessarily, and what we know are the expectation values, which we compute by taking a trace of rho times each of these observables. Okay. And then we can, in principle, define what I will call the Jaynes density matrix. Which has two properties. First of all, it reproduces the known expectation values. One property. And then, subject to these constraints, and of course it also has to be properly normalized, so its trace is 1. And then it maximizes the von Neumann entropy as a function of rho. I won't put the J there. So again, the idea is the Jaynes density matrix correctly reproduces the known expectation values, is correctly normalized, and otherwise maximizes the von Neumann entropy. So again, thinking of von Neumann entropy as an amount of missing information, this is saying we will think of the system as having a density matrix which reproduces what we know, but doesn't do more than that. And we will measure that it doesn't do more than that by maximizing the amount of missing information. So, question?
I just understand how it works. So, for example, if my observables are just, say, the Hamiltonian and so the total, then this would produce something like the thermal density matrix.
Yes. Yeah.
Whereas if I have like a lot of information about the observables, like all the micro observables, then it would come very close to the actual microstate of the system.
Well, it's actually easy to solve this problem by Lagrange multipliers. So the way we solve this is we define an S tilde, which is minus trace rho log rho. But then I put in Lagrange multipliers for each of my constraints. So I have sum over I, however many observables we have. And I also put in a normalization constraint. And so the lambdas and omegas are Lagrange multipliers, and now we vary S tilde. If we vary it with respect to one of the multipliers, we just get back our constraint. But if we vary it with respect to rho, schematically, let's see, we get minus log rho. Plus, minus, I think it's minus 1, I guess, right? Okay. Plus lambda I AI plus omega. And so we're trying to maximize it. So we set this to 0. And so the solution is that rho, I'm going to write it like this. Where Z is and Z is basically e to the omega minus 1 or something. Okay, so that's the solution. And of course, as you just said, if the only, and let me just say, the values of the lambdas are then adjusted so that we get the correct expectation value. So if the only A is H, then rho, and then we conventionally now rename lambda beta, we just get e to the minus beta. Okay, and now you can check that this just
Sorry, can you comment on what happens if I have a lot of AI?
Well, yeah, I mean, if your AIs are, a simple case would be that your AIs are projection operators that are projecting you onto specific states, right? And then, because AI squared is AI, we can just rewrite the exponential as a product, and eventually, I think we will land on something that projects onto a specific state.
Maybe physically, I would want the AI to correspond to, say, local operators.
Yeah.
Something like that.
Yeah.
Yeah.
Heavy operator.
Well, I mean, this all assumes I can do things like take traces and so on and not run into infinities as we might in some quantum field theory. So we would need to do some suitable renormalization, possibly, to define.
What's the meaning of the equation of the solution to the formal equation? So let's say rho.
I'm sorry.
I think about rho is a matrix.
Yeah, but okay. So I can diagonalize rho here. Yeah,
It's a bit, I mean.
Yeah.
So I think about that. You're diagonalizing it, and then I can think about
Yeah.
let's see what's a matrix and what's a scalar. Because
Yeah. So this is all. We could come in here and we could put indices on everything, right? So I'm doing it schematically here, but if you do it more carefully, you get the same answer.
okay, so omega doesn't play any role in the.
Omega got absorbed into z here. So z is something like e to the omega minus 1, or maybe that's 1 over z, something like that. Right, because if we just strictly follow this, right, we'll now have minus omega plus 1. But I want to conventionally call that, right, but the role of omega, what is omega doing? Omega is supposed to be enforcing trace rho is equal to 1. So I will, if I now declare that e to the minus omega plus 1 is 1 over z, and I define z like this, rho will now be correctly normalized. So omega has done its job. And the role of the lambdas is to make this true. So we have to choose the value of the lambdas, which give us the correct known expectation.
How did the temperature get up in the exponent?
Beta is, I just renamed, so lambda h, I'm now calling beta. We don't yet know that it's a temperature, right, or an inverse temperature. This is all just, but I'm about to show you that it's an inverse temperature. Okay, and so what is the von Neumann entropy? I'm just going to call it, or Jane's entropy now. I guess we should call it the von Neumann entropy as computed with the Jane's density matrix. Well, the nice thing about this form is it's easy to take the logarithm, and so if you compute this, you will get log z, and z we should think of as a function of the lambdas, and s we should think of as a function of the a's. Maybe I'll specify to a single a here just to, so I don't have to keep writing the indices. And then there'll just be a plus lambda a, because when we take the log of rho j, this is minus log z minus lambda a, and so now I have the trace of rho j times a, but that is just this expectation value little a, and the minus signs cancel. And so if you look at this structure, I'll just write it over here. If you look at this structure, this is the form of a Legendre transformation between lambda and a. And so what that means, in particular, is that if we take the derivative of s with respect to a, we just get lambda. So you can see that If you don't remember how Legendre transformations work, and Legendre transformations are one bit of math that I was never very good at internalizing, so I always have to work it through myself anyway. So how does that work? If we take ds dA, I have to differentiate this. That will give me a 1 over z. But z depends on lambda, but then lambda depends on a, because I have to know, to decide what lambda is, I have to first know what a is. And then I have to differentiate this. Differentiating the a is easy, but then I will also have a but z, remember, is trace e to the minus lambda a. So dz d lambda is minus trace e to the minus lambda a. But this is just up to a factor of z, the expectation value. Okay, so then this z cancels this 1 over z, and this minus a cancels this, so these guys cancel each other. I'll move this up. Sorry? Lambda. Excuse me. I told you I don't understand Legendre transform. Okay, right. So here's, and so now if we come back to the case that the only A is H, we can, and of course we call the expectation value of H, and we'll call it the energy. In this case, we just get ds dE is beta, and if we remember Clausius, the differential, the change in energy is TdS, where T is the temperature. So if we compare these two things, we conclude beta, and if we put back Boltzmann's constant in the right place, that beta is 1 over K. So this then connects conventional thermodynamics, if you like, and the Clausius entropy to this more abstract information theoretic entropy. Maybe this is a good time to take a break. How long do we want to break for? How long do we break for?
15 minutes.
15 minutes. All right. So 11:10 we'll start.
Yes.
All right. Thank you. And happy to discuss if there are any further questions.
Okay.
È quello che sto qui. Ma anche su Zoom, se no.
A questo punto se io switcho da questo, Zoom non sento.
No. Zoom non passa tutto per via.
No, quindi io faccio così.
Questo stai semplicemente spegnendo YouTube e la registrazione, quello è un'altra cosa.
No, perché Zoom capta quello che gli manda OBS.
No, solo il video.
Okay.
Tra l'altro non fa segni quando dovrebbe mostrare
I think I
qualcosa.
just mentioned the interpretation way
Quando arriva un suono, no? qualche segno per dirti che
Oh, no, all it tells us is that is this.
It's not a problem.
in BBB fa una cosa tipo questo, cioè c'è un log
Yeah,
dovrebbe essere un microfono.
It was Gabriele. Okay. Sorry, I didn't remember all this.
Thermodynamics presented sort of axiomatically. This is a function of that, and that is a function of this.
I follow some online and
Holding things. So the right way to think about it is that we should think of S as a function
Una volta che andiamo al ristorante
but we should think of
con i problemi.
Io così testato ieri.
Yes.
Mi sono testato ieri perché
S and log Z
ho testato ieri perché anzi l'altro ieri stavo
Stavi male.
means that
mi sono testato e sono negativo.
derivative of S
Antigenico?
and similarly the derivative with respect to
Allora non so,
lambda of log Z, now I think there's a minus.
Sì, chiamaliamo il speaker per
Yeah, okay, so
Back and forth.
and this gives the lambda, the
Così oggi sto bene, ma
Yeah, it gives it a physical.
term, what do you mean? Io non so stamattina, ma va bene, non è... But why is this without summing over the indices? Riccardo, cosa ne pensi tu? So what do you mean second term? So it's the exponential state of the system. But I don't understand the connection.
Yeah, no, I mean, it's not supposed to be clear.
È positivo.
Non sono positiva.
Lui?
Lui non lo sa perché ieri era troppo stanco per andare a farsi.
Quindi è positivo.
Non so cosa, forse ha.
Io sono
tante
pessimista.
malattie, ci sono tantissime malattie fuori del Covid. Perché prima del Covid avevamo delle altre.
No, ma secondo te c'è il Covid o no?
Non ho idea. Ma l'epidemia basta, sta.
io devo vedere la mia visita che è stato mercoledì.
Che predica il futuro, un attimo. 1%.
Diciamo, se lui è positivo, io vengo e dopo ci sono le problemi. L'unica cosa.
It should start from zero. It should start from zero place. It should do something. And it should
E il mese basta.
Il testo cambia il giro. Sì, ma lo sai come funziona?
No, più che altro per Marca, che poi dovete andare negli stati.
Sì, dopo si ammala questo weekend.
Lui mercoledì torna negli
C'è un casino per ritornare agli Stati Uniti. Noi agli Stati Uniti domandavano un test negativo. Ah no, non per gli americani. Sì, ho dovuto pagare 800 euro in più perché per entrare non avevo il
corrotto
No, guarda che paga, mi ha pagato alla fine 800 perché cazzo di mi ha domandato 800. Un giorno, il giorno dopo ero negativa già.
Credo che non ti chiedono il vaccino se a posto.
Io avevo il vaccino. Non sei di
Adesso.
In our paper at the end,
perché sei stato? No.
No,
No, ma senti,
No, ma io sarei cioè se c'hai paura
diciamo, a me non mi frega, ma se lui si ammazza,
perché lui deve
Perché uno
partire, anche
solo-
Pier Francesco deve partire. Non vai per
in Svizzera e domenica prossima vado in
Ah,
drop that.
sì, diciamo sono più
almeno non ti sei
iscritta per
Status of it all.
che per
I think
guarda, comunque andiamo
diciamo sarebbe una una stronzata. Mettersi su una scherma, sì, assolutamente.
Pause, on fait pas de micro, auditeurs ensemble,
On l'a coupé.
Ah bon, parce que là, moi je viens de monter, je descends juste pour vous le dire, c'est tout. Il est coupé?
Non, on n'a pas coupé le micro, on l'a coupé ici dans la...
On a coupé là.
Moi je suis sur YouTube et j'entends tout.
Sur YouTube.
Non, mais
Ah bah,
Non, c'est parce qu'on parle en langue,
non, mais en fait,
en italien.
tout le...
On croit qu'on avait bloqué, là c'est bloqué, et ici c'est en pause, doucement.
Ah, mais si.
Vous vous connectez pour vérifier? Oui.
Sur YouTube. YouTube, IPhT-TV, t'entends tout ça.
Il va falloir...
Mais quand il y a bonjour YouTube. Quand il y a la course, non.
Alors, ça marche pendant les cours?
Ouais.
Comment ça s'affiche parce que je regardais 2 vidéos en YouTube et je trouvais que c'était un peu dur de lire ce qu'il écrit au tableau.
Mais même le deuxième.
Et je crois que c'est justement parce qu'on fait ce partage d'écran avec 2 vidéos, écran vidéo,
Je sais pas si...
ça empêche que...
Je sais pas si... Faut être un petit on sait pas ce que c'est. Mais comme le son, je mets le son en table de fond, mais ça va, il fait une table de fond. J'ai vu qu'à la pause, il y avait... Voilà.
Le premier cours c'était dans l'autre.
Non mais sinon, on va vous essayer les télécommandes et t'appuies sur un bouton et...
mais je l'ai coupé, mais...
Et après, il y a un problème parce qu'apparemment,
Je l'ai coupé. La chose que tu peux mettre, c'est pas ça.
la qualité
Ah non. Ah ok.
On va avoir le petit...
Alors, non, mais la réponse est que normalement, on préférait...
Non, ça marche. Io ho messo il
Attends, je te dis.
Normal, ça fait partie du...
Un vidéo d'hier et voilà.
Ci sono altre...
No, ok, maintenant ça marche.
Regarde, mais...
Non, c'est en direct, mais parce que tu renvoies sur les serveurs. C'est pour ça que tu ne veux pas l'intégrer. On décale.
Allora,
Vous amenez une télécommande
tu vai giù. Sarebbe una buona idea di...
La clé.
Donc,
c'est
global,
C'était quoi que tu mentionnais sur l'écran?
Non, je pense... écoute, là, on voit bien. Ok. Je pourrais réallumer les deux, mais on voit bien les formules.
Oui, c'était juste pour confirmer ce problème.
Mais comment on coupe les micros? Parce qu'effectivement, YouTube, on entend. Donc là, j'ai coupé.
Oui, tu l'as fait dans les...
Donc là, c'est... Donc pourquoi?
Non, mais attends. 20 secondes.
Non, je l'ai coupé. Ok, je l'ai coupé là, mais sur YouTube, il est encore là.
Ah, il rentre avec desktop audio,
peut-être.
On peut pas agir au niveau du mixeur Linux.
Si. En principe, tu peux le couper là. En fait, ce qui se passe, c'est que quand tu le coupes là, ça le coupe. En fait, le micro, les chiffres par OBS, en parallèle par Zoom. C'est deux choses à part.
Mais là,
Perché faccio OBS.
Genre 2000 € la
Ah, io...
Bah non,
La
mais
scène tourne.
Moi, allez, 110 secondes.
Logiquement,
Sometimes the car move in the position. Yeah, so now it's
pas trop bidouiller parce que
yeah, maybe it was just one.
So the first video it was a bit in Ansible.
In fact, there were a problem. Also, I remarked that the middle blackboard was okay, but the two black were not okay. Yeah, I don't understand why.
il y a que ça comme.
So the first one was
If one would make this just take one time.
Ouais, en fait, c'est le micro, tu peux le piloter d'ici aussi.
Et là, il y a
Ah oui, oui, mais... Il va repasser bleu.
Ok, ça va.
Donc quand il est rouge, il est vite. C'est les premiers pas, c'est les premiers essais avec ça.
Donc cette chimie-là, c'est pas nécessaire en fait. Ça veut rien.
Ben, ça devrait. Il faudra qu'on regarde.
Ok.
On va faire, voilà. Ça devrait. Non mais en fait, c'est ça. C'était juste des choses compromettantes tout entendant.
Ça fait un chapitre.
Ça fait pause, ça fait pause. Voilà. Bon, faut le casser, ça on l'enlève. Je sais pas, c'est pas un virus. Je peux juste vérifier un petit truc. Tu peux ouvrir un chèque. Non, vas-y.
Alors, vous avez besoin aussi.
Ah ben, je sais pas, il y a des choses techniques. C'est un Maxime a priori. J'ai quel Maxime? Je sais pas qu'est-ce qu'il faut expliquer. Non, je sais pas. Il y a son nom ici. Ok. Ça va, c'est le même. Non, je pense que voilà.
Non, et on peut pas faire point. On arrive à 700. Non, mais c'est stable.
Qui c'est qui est monté là?
On peut faire l'analyse de pied, mais
C'est pas moi chaussure, c'est moi non plus.
ça va être Maxime.
Non, ce qu'il faut qu'on fasse, nous, c'est qu'on...
Non, mais tu comprends le problème du
Ben moi je vais mais ils ont je vais couper le son actuellement, pour l'instant, le plus simple c'est ça.
Ouais, mais ouais. Je savais pas, mais et là,
peut-être en plus,
Là, ce que je ne comprends pas, c'est si on coupe là et on coupe à la main en zoom, pourquoi il doit y avoir du
So
son?
when people talk about the
Early on, I thought people would have.
C'est la chose. En tout cas, la phase de test, il faut rentrer.
Nevertheless, we declare the system what we call the entropy of the band. Somebody else was because they're different objects. They're not the same. Okay.
I don't understand why I have. No, that's a loop. Okay, that should be killed. 1 second, please.
Non, c'est bon.
Et là, l'hai fatta?
Oui, oui.
No,
oui, là,
muta.
il faut le faire.
A mute, quoi.
Oui. Ok, c'est bon.
Okay.
Okay, we're back. Yeah, so last time I was really just running through a more or less conventional stat-mech presentation focused on entropy and what I like to call the Jaynes entropy. So again, in the case where the Hamiltonian is the only observable and the expectation value of H, called the energy, is known, this rho being whatever the true quantum state of the system is. But we don't know the details, we just know it's energy. Then we write down not the actual system density matrix, but what I call the Jaynes density matrix, which is the density matrix that once beta has been correctly chosen, correctly reproduces the known expectation value and otherwise maximizes trace rho log rho, and then we get this answer. And then we see that, again, just by doing the math, and now I'm writing total derivatives because there's only one variable here. The derivative of S with respect to E is beta, which we then identify as 1 over, we put in Boltzmann's constant kBt from thermodynamics, and the Legendre transformation tells us that it also goes the other way. If we differentiate log z with respect to beta, we get minus E, which is also deducible. So I guess I should say the Jaynes entropy, or Jaynes density matrix correctly reproduces the energy. Okay, but now I also want to connect this to Boltzmann and to S equals log W. So if my system, and now we'll finally come back to energy eigenstates, has some energy eigenstates, we can define a density of states, which I will call WV. In which we just put a delta function spike at every actual energy. In many systems of interest, this will go up to infinity. But now we can imagine doing some smoothing. So instead of a bunch of sharp spikes, we smooth it over some range of energy, which has to be chosen to encompass many spikes, but we want it to not vary too much as we change the energy. So we can have a smooth WC. And the claim is that the smooth WV is the exponential of the entropy, this entropy. And usually I don't worry about this. The delta function has dimensions of 1 over energy, where usually I just write W as e to the s, but if we want to be careful, there's something with dimensions of energy that goes here, which we can think of as just some energy scale characteristic of the system. In the sort of many-body systems we're interested in, S will scale like the number of degrees of freedom, and so whatever comes out here is some subleading thing in terms of the number of degrees of freedom, and so we really don't have to worry about it too much. But that's something that might bother you. Okay, so now we want to see, and this is really a quantum version of Boltzmann's argument, but Z is trace e to the minus theta h, which is now just a sum on the eigenenergies, but using this, and I'm assuming the lowest energy is 0, we can rewrite that as this integral, and if we plug in the delta functions and go right to left, we'll just immediately get back to the sum. Okay, but now I want to make this smoothed approximation and write this. I'm going to ignore this epsilon naught here. And now again, for a many-body system, we have some measure of degrees of freedom. I want to think of the energy as scaling with the number of degrees of freedom, and it's just generically true that the density of states is exponential in the number of degrees of freedom also, which you can easily check for simple systems like n free particles or n harmonic oscillators or anything like that. Okay, so and we're thinking of both these quantities as large, so now we can do this integral by Laplace's method, using the technically correct term, but it just means we find the point in energy where the exponent is stationary, and then we evaluate the integral at that point. And then we can, if we like, I won't bother to do this, but we can do a more refined calculation where we compute a prefactor by doing an approximate Gaussian integral. I'm sure you've all seen that kind of thing before. Laplace's method. So I really want to call steepest descent, but technically isn't. We just evaluate the integral, evaluate the integrand at an energy E bar, where E bar is the value of the energy that makes the exponent stationary. Of course, if we work out what this is just covered up. I guess I can pull down the other board here. Okay, which is just the conventional thermodynamic relation. So, and once we've done this, we've now evaluated Z, so we can write log Z of beta, if you like, is S of E bar. I think I have a sign. No, the sign is right. Okay, that sign is different. All right, and where again, well, now I'm calling it E bar instead of E, but again, this is exactly the thermodynamic relation between energy and temperature. So we just reproduce all of this stuff we had before, but now we identify, in accordance with Boltzmann, that this density of states, W of E, is the exponential of S of E. So,
the systems cannot be complex saddles.
I'm sure one can find a system where I don't know. I hesitate to make a comment about all possible systems. In the simple things we think about, it's just a real solution. All right. Okay. What about the notion that entropy should increase? What does that mean? Let's see. All right, so now, so we can think about the time dependence of S in the following situation. I want to imagine now that I have observables are H and a time-dependent observable A of t. So I'm imagining in a Heisenberg picture, we have some non-constant observable A, and it evolves in time. And what I mean by known is that, maybe I should put the known here. And there's some exact quantum state. And I'm going to think of it as a pure state because that's the discussion we've had in the ETH context. It doesn't have to be pure. If you want to replace this by a more general density matrix, go ahead. And what's known are the expectation values of H, which is, of course, conserved. So this is a time-independent energy. And, well, I guess now I've gone to a Schrodinger picture here, but maybe I'll just write it. I probably shouldn't have written down the Heisenberg picture. Okay, so the idea is that we somehow know the time-dependent expectation value of A. Now, this is a theorist's caricature because if you went into somebody's lab and said, please measure the time-dependent expectation value of A for some initial state, they would have to do a huge amount of work because you would need a zillion copies of your system, each in the identical state. You would then time evolve it for time t. You would measure A, but that doesn't tell you the expectation value. That just tells you one sample. So then you would need to do that 1,000,000 times up to time t, write down the average. And then you would need to do it again for a second later, and then again for a second. Okay, so nobody actually does this. This is a theorist's caricature to say that we know this. Nevertheless, I think it's useful to think this way, and I'm going to think this way. Okay, so now what happens, according to all of this stuff that we've been doing, we would now write down a Jaynes density matrix which would look like this. Actually, I should try to find this. We would now write down a Jaynes density matrix, which, because we've specified our two observables, H and A, would have the Jaynes exponential form. But now, because we're doing this moment by moment in time, our Lagrange multipliers are going to be in general and usually specifically time dependent and adjusted moment by moment in time so that trace rho j and trace rho j. Well, I guess now I'm using the Heisenberg version. I think there's some embarrassment. Okay. Is there a question? Yeah.
Yeah, so I didn't get why beta depends on t.
Oh, just you don't expect it to depend much on t, but if you like, you can think of this as, you can think of A as some sort of chemical potential. So I'm changing the Hamiltonian. So if I change the Hamiltonian and I want the same energy, I might have to adjust the temperature a little bit. But if H is an extensive quantity and A is some single site or few body observable, we wouldn't expect beta to change much. But in principle, because we are effectively changing the Hamiltonian, we also have to change beta. Okay, and now I think we have to input some real dynamics, and that not inputting real dynamics was a missing piece of the Jaynes description. But if we now declare that our system obeys ETH and A has the ETH matrix element structure, the whole ETH story assuming then the whole story that I tried to convince you of in the previous lectures is that if that's true, for a very generic quantum state, even if we start off far from equilibrium, and here is some thermal value of A, which is this, and where now again beta has been adjusted now to give the correct energy, that very generically, doesn't matter, the details of your quantum state don't matter. it will do this. It will come down, possibly wiggling to a thermal value, and then stay there most of the time. So the system, quote, thermalizes, unquote, according to this observable. It moves to its thermal value and then stays there. So if we assume that the system thermalizes according to this, we can now ask what happens to the entropy on the same scale. And the key point is that if the actual expectation value is equal to the thermal value, that tells me that the corresponding lambda is 0. I compute the thermal expectation value just using e to the minus theta h, and I don't have a lambda. But setting lambda to 0, this removes a constraint. On the Jane's density matrix. If the answer is that lambda is 0, that means it's equivalent to not having imposed that constraint at all. And loosening a constraint or removing a constraint means that the entropy can be larger, right? Because the whole Jane's density matrix is constructed by maximizing the entropy subject to the constraints. If you remove the constraint, one constraint, the entropy can now be bigger. So what that tells us is that if we plot the Jane's entropy, minus trace it will start at some value, but then on exactly this scale, we should expect it to come up and now just be the usual thermal. Because, going from this point to this point where we've effectively reached the thermal value, we've removed a constraint, and so the entropy has to go up. Now, proving that it has to be monotonic, I don't quite know how to do that, but in some heuristic argument, we're making the constraint weaker and weaker, and so we would generically expect the entropy. Okay, so this is an entropy whose definition depends on what we've decided to track. We've decided that we know this instantaneous expectation value, and then this information theoretic entropy behaves in the way we would expect a thermodynamic entropy to behave. It increases with time and then moves to the thermal value, and that's it. Question?
We want to think about this as removing a constraint. I mean, can't we just solve the system for, assuming that A at some time becomes the thermal guy, and then we automatically see that. It's not satisfactory because we don't have to do it by hand, but it just comes.
Yeah, I think, yeah, I agree. I mean, the removing the constraint argument just allows you to draw the conclusion without doing any work. Right?
So I guess we can about this Jane's entropy with particular A operator.
Particular A,
so
right.
If we ask the same question, but working with linear or Neumann entropy and just some operator A with ETH matrix elements, the picture will be.
Well, if by the von Neumann entropy, we mean minus trace rho log rho, where this is the actual density matrix, the actual quantum density matrix. This is conserved in time. Right? So this is time independent. And if your state is pure, it's 0. So this is a very uninteresting quantity. Okay, so it cannot be the thermodynamic entropy. my claim is that it's the Jaynes entropy that corresponds to the thermodynamic entropy. And the Jaynes entropy, as I was discussing with one of you earlier, the Jaynes entropy really depends on what we've decided we know, right? We have to know what we know. And if somebody else knows something else, they will compute a different entropy. But that's fine. They know something we don't know, and it's just a different object. But all of these entropies, assuming everybody's variables, maybe somebody else has a b of t, and maybe it takes longer, right? But to the extent that that all the observables that we can consider tracking, and in practice this means few body observables in a chaotic system. If they all eventually thermalize, then somebody, we could call this SA, somebody else would then have a different entropy, and that will have a different path, but it's a different object, so it's okay.
It could start lower, for example.
It could start lower, right, and should, right? Now, if we know B, we know more, so it's lower.
Some characteristic time for implicit entropy is determined by the characteristic time for the observables?
Yeah, it's determined by the thermalization times for the observables, which is highly system and observable dependent.
Something like more or less universal instead, or not at
Well,
all?
we have to know the system and we have to know the observable and what it does. The claim is that if your system is such that your observables thermalize in the sense that they move to thermal expectation values, then the corresponding Jaynes entropy will rise to its thermal value. Now, to know whether this actually happens, one needs to know what your system is. Do the matrix elements have the ETH structure? If they don't, have you picked a state where this is going to happen anyway? And so now there are a million questions, right, for any specific system.
I guess the question was more like if there's a special set of observables whose time relaxation would also tell us about the time relaxation of the Jaynes entropy.
I'm going to say no. I mean, so if we have a gas of particles, the thermalization time is set by something like, a mean-free collision time, plus some amount of time for collisions to propagate through the system. So it really depends on the details of the system, how fast things happen, right? This is the only claim here is that the Jaynes entropy will approach the thermal entropy on whatever time scale your observables approach their thermal values. And you have to tell me what that is for your system that you're interested in.
Sorry.
Yeah.
More or less similar question.
Yeah.
Can we say anything about the order of magnitude, for example, compared with the total entropy or compared with the number n of degrees of freedom?
Well,
about this thermalization time. For example, it should not be exponential in the number of degrees of freedom.
No, if it's exponential, that means that, it's not thermalizing, right? So, we know that systems can have fast modes and slow modes. People try to derive hydrodynamics from some underlying thing, and the hydrodynamic modes take longer. It really depends on what your system is and what your observables are. And early on in this business, I would give these general talks, and somebody would come up to me and say, "What about system X?" And they would inevitably be the world's leading expert on system X, about which I would know nothing, right? And so, but they would have identified some slow mode in system. All right, so this is a very general analysis, which is a two-edged sword, right? A general analysis tells you general things, but if you now want to ask specific things, it doesn't help, right? So all I claim is that if your observables have an ETH matrix element structure, this will happen. But this time scale is really going to be controlled effectively by a Fourier transform of this f function that lives here. Right? Okay. So now we have to know what the f function is for a specific system and a specific equation.
And so since last time we showed that this is linked, one can link these coefficients to the bound on chaos. Can we at least say, even if we don't know the time scale, can we at least say that these two time scales are the same? Like the time scale of this thermalization and the time scale of chaotic behavior are similar, or one is larger?
No, and in fact, to get the OTOC, you actually need a separation of time scales. There has to be what Maldacena, Schenker, and Stanford called a dissipation time scale, which is what I would say is this time scale. And then, so the dissipation happens fast, and then later there's an OTOC that builds up and then stops growing exponentially at what they call a scrambling time. So that actually relies on a separation of time scales, which one may or may not have. In general, for that, one needs a small parameter, and e to the lambda s is 1 over the small parameter, or lambda scrambling time is 1 over the small.
Can you relate what you did with Lindblad equations?
I'm sorry?
Can you relate what you did with Lindblad equations?
With the Lindblad equation. Yeah, well, Lindblad applies to open systems where, and this is the usual setup for the Lindblad equation. You have some system where you've coupled it to something else, and then you model the coupling to an environment by the Lindblad operators. So one could ask, could I think of the degrees of freedom represented by these observables as a subsystem, and then try to write a Lindblad equation? I have never tried to do that, and as far as I know, no one's done that in a controlled way. I mean, of course, we could do it in an uncontrolled way where we just declare that, well, that should be a Lindblad equation, so let's write one down. But I don't know that's a good question, though. I don't know a controlled way to do it. Doesn't mean there isn't one. I just think.
I guess what's nice about this entropy is that in the end it gives you the thermodynamic entropy, which you cannot get with the normal von Neumann entropy of the exact state.
Right. The von Neumann entropy of the exact state
is just zero.
It's zero for a pure state, right? I mean, and in a mixed state, it's just some pi log pi, and it's constant in time. So,
can you somehow put this change and the change of the James entropy in contact with the thermodynamic entropy? So can you somehow say something about thermodynamic classical behavior of the system?
Well, I mean, I think what I've tried to spell out is that these starting from this information theoretic notion, and then we then define the James entropy as something where we know some set of quantities. And then we find out that if the known quantity is the energy, and all other quantities agree with their thermal expectation values, the James entropy is the thermodynamic entropy. And at this point, I just declare victory and say, great, we understand it,
Asked about James entropy and similar pictures for integrable model doesn't have sense because there will not be such a TH.
Yeah, if you're looking at observables that don't thermalize, your entropy will not. Integral models where you declare you're tracking, the integrable quantities, right? Now, in things like interacting integrable systems where I may say something that's wrong. But yeah, one has to think about exactly what one is tracking and so on.
And what if we don't track all these degrees of freedom?
Oh, well, if you don't track, and you just declare that all you know is the energy, then you will conclude that the Jane's entropy is the thermodynamic entropy, and you will look at your box and say, I'm not going to measure anything, but I'll just assume it has the thermodynamic entropy.
What about the Renyi entropies computed with the Jane's density?
I mean, I assume they behave the way they're supposed to behave, but you know, the Renyis don't have the, you know, why is alpha equals 1 in the Reny's case special? I think it's special because that's the case where it's additive, right? So there are these, you know, additivity identities that have been proven about entanglement entropies, but I think those don't hold for the Renyi entropies. So it's really additivity that's sort of the key principle. And the Renyis are just useful because they're often easier to compute. And so I think if they weren't easier to compute, we could just ignore them and never discuss them.
So how is this, like this quantum mechanical sort of derivation of thermodynamics, how is this related, for example, to like when you instead don't do quantum mechanics, but you do like stochastic thermodynamics, and for example, you have like some Fokker-Planck equation, which then converges dynamically to your space-based distribution? Like, is it just that we are saying, okay, we don't know the quantum mechanics, so we just say it's stochastic, and this is the underlying reason, or are they like separate?
Well, I don't know much about stochastic dynamics and Fokker-Planck and all that. So to the extent that that's intended to model some true underlying system, quantum system, as opposed to being something we create, you know, ab initio, I would say it should be the same. But
do you plan to discuss the relation between the thermodynamic entropy and the von Neumann entropy of a subsystem?
Yes.
Okay. Thank you.
As soon as the questions stop, I will. Okay. So. So yet another thing we can think about is we have, and now I'm thinking of a system like a lattice system or something where we have degrees of freedom that are localized in space, and this is the space, and we have a complete system that we're going to divide into two systems arbitrarily. Subsystem 1 and subsystem 2. And again, I like to think about spin systems or things like that where I can specify a complete set of operators that live in subsystem 1. So we can have operators that live entirely in subsystem 1. We can have operators that live entirely in subsystem 2. And then we can have operators that in some sense live on the boundary and have connect degrees of freedom in both subsystem 1 and subsystem 2. But I want to think of few body degrees of freedom. So just things that live on the boundary, I want to think of them as living near the boundary. So if I now declare that I have a set of observables which is a complete set for subsystem 1, I can now And I have a state rho, a density matrix, which is the exact quantum state of the whole system. I can now define a density matrix for subsystem 1, which I define, which I'll do rather schematically here, by saying I'm going to take rho and I'm going to trace over all the degrees of freedom that live in subsystem 2, and I guess I'll include the boundary ones in that. But we can think of this as the Jaynes density matrix given the AIs. That is, if I have a complete set of observables, that means what I mean by a complete set is that trace rho 1 AI, this set of values allows reconstruction of rho 1. If I know these expectation values, I can go back. I have enough information to go back and reconstruct the complete rho 1. Yeah.
So I'm assuming that the total Hilbert space can be written as a tensor product of the one.
Yeah, I'm assuming some, whatever simple.
Well, it's just that for many applications, for example, gauge theory or even particle theory, if I understand correctly, the Hilbert space is not separable. So can you comment on?
I can comment by saying I'm completely ignoring such issues. And,
but some people,
many people are very legitimately interested in such issues, but I am ignoring them.
Okay, let me ask differently. Is there a definition of the entanglement entropy that's appropriate for quantum field theories without saying symmetry?
Well, again, many people have discussed this, and in particular in gauge theories, one has to worry about what's happening on the boundaries. And again, this is beyond the scope of what I'm trying to do here. I'm trying to do something very simple. But those are completely legitimate and important and difficult questions. I do not mean to dismiss them as unimportant. Okay. Right. So this notion of all right. So then we can think of rho 1 as a specific example, some sort of extreme example in a sense of a Jaynes entropy, where I know all the observables inside here such that I have enough information from their expectation values to reconstruct rho 1. Now we can now compute an entropy, a von Neumann entropy for rho 1. Okay, and this is what's usually called an entanglement entropy. And in particular, the entanglement entropy is an interesting thing to think about in the case of a pure state for the system state. So if we initial row is pure, the initial row is pure, there's a theorem you can prove, which is, and again, this is in the context of finite dimensional Hilbert spaces, and we can worry about what happens in more complicated cases. We can write down two density matrices, a density matrix of subsystem 1 or a density matrix of subsystem 2, and the theorem for finite dimensional Hilbert space and here, as drawn in the picture, I'm thinking of subsystem 1 as smaller than subsystem 2, and so in particular the dimension the dimension of row 1 I'm thinking of as smaller than the dimension of row 2. The statement is that the eigenvalues of row 2 are the same as those of row 1 plus extra zeros, because it's bigger. So. But that in particular means that the trace of, well, really any nice function, but I'll just write it as a power, I guess I want alpha to be positive here, so we're not trying to take 1 over 0. And so in particular, this means that all the Renyi entropies are the same, and the entanglement entropy is the same. So the entanglement entropy, defined in this way, we could call this S1, and similarly S2. These are the same if the state of the system is pure.
So is this like saying, like, for example, going back to the box at the beginning of the lecture? Okay, so there we would like to say now that if we know information about a very small number of boxes, then the information that we're missing is bigger than if we knew about the larger amount of boxes. We divide the n boxes into subsystems, 1 and 2. One is very small and one is very big. We would like to say, just by common sense, that the information we're missing, if we only know the small part, is bigger than if we only know the big part. So,
right, and this is not true here.
Yeah.
Okay. So this is violating that intuition. And
this is because pure states are very quantum mechanical.
Pure states are very quantum mechanical. Yeah, I think I would agree with that representation. Yeah. And so what this is telling you, I think, is that it has more to do with the boundary between 1 and 2 than it does with 1 and 2 per se. And so, in fact, a simple, well, may not be simple, but a thing to think about is to let rho be the ground state of the system. And how should we think about a ground state? A ground state, the ground state knows about nearby points, and so the ground state is going to produce correlations on some scale. So if we think of two operators, it doesn't really matter if they're let's call one A1 and another one outside here A2, and there's some distance between them. We can imagine that maybe this will fall off like some distance over some sort of correlation length, that there's some finite correlation. Or maybe it's a power law. It doesn't really matter. But it's going to fall off with distance. And so what that means is that when we take the trace over subsystem 2, all the stuff that's out here doesn't really matter very much. We're tracing over that, but the only things that influence what's happening here are things that are within this correlation. And so we can then guess that this entanglement entropy, which is, again, it will now be the same whether we trace over subsystem 1 or subsystem 2, that this scales like the area of the 1-2 boundary. And so this is called these days the area law of entanglement entropy. It was first written down in 1986 by a group, Bombelli, Kuhl, Lee, and Sorkin. Sorkin had some unpublished work earlier where he wrote it down, but publish or perish, right, if you have an idea, publish the paper. But, they did publish it later. But their paper got very little attention. And in 1993, I think, I started thinking about this in the context of black hole entropy. And black hole entropy famously scales like the area of the black hole. And, and Bombelli et al. Were also inspired by black holes. And they pointed out that this sort of entanglement entropy, it's natural to expect that that scales like the area also. And then having not read their paper, rediscovered it. And also one can do simple calculations. So I was able to do a calculation with a set of coupled harmonic oscillators in which one can actually demonstrate that this is true. But it really just follows conceptually from this notion that in the ground state, we can expect correlations to fall off with distance. And so only when we trace things out, only things that are near the boundary in subsystem 2 matter. And so that will naturally produce a result that scales like the area. Okay, but the ground state, and this, okay, so this is interesting for a variety of reasons. But the ground state is not what we want to think about when we think about thermodynamics and ETH. For ETH, we want to be higher in energy. We want to be at a finite energy density. And so now we can ask the same question. What if instead of the ground state, we look at a state of finite energy density? And so various people, including me and my collaborator Chaitanya Murthy, thought about this. Also Tarun Grover and his then student Peter Liu. But I see I've got like 5 minutes left of the hour. So I think I will stop here and I will tell you that story on Monday, for those of you who are able to come back on Monday. And meanwhile, I'm happy to take more questions, and I hope everyone has a great weekend.
Thank you. More questions? Who's on Zoom? Yes, please.
Yeah, I mean, I guess maybe. I mean, I think one would need to formulate what that means a little bit more precisely, and then I think there's probably a precise version of that question to which the answer is probably yes. But I would want to sit down and think about exactly how I would want to formulate that. But it sounds very plausible. Yeah, so spoiler alert for Monday. The answer is, not too surprisingly, that for a finite energy eigenstate, rho 1 just looks roughly like a thermal density matrix for the Hamiltonian in subsystem 1. But there are some complications and some subtleties, and so we can't just immediately write this down. So I'll talk about that on.
Should we think about like the total entropy, let's say, of a subsystem as a sum of some thermal entropy plus entanglement entropy?
Yeah, probably. I mean, so if we take a limit, right? So where the whole thing is very big, and subsystem 1 is very big, and I can ignore surface to volume corrections, right? So in that limit, so in the limit that the volume of subsystem 1 goes to infinity, and the volume of subsystem 2 goes to infinity, and the volume of subsystem 2 over subsystem 1. Do I have to take that to infinity? Yeah, probably. I don't know. But when everything gets big. And so I can think of subsystem 1 as the interior of the room, and I'm far away from the wall. Then this is true. But even if I'm talking about a box of gas in the lab, in principle, I have to worry about what's happening at the walls and so on. So I don't think, yeah.
So you're saying that in the thermodynamic limit, still the thermal entropy will be much larger than the entanglement entropy.
Yeah, because the entanglement entropy, well, if we define the entanglement entropy, in a sense, whatever I get here, right? So if you believe this, I just call it the entanglement entropy no matter what rho is. But, if we do it in a situation like this, and we're careful, there will be terms that scale like the volume that will look thermal, and then there will be other terms that scale like the area. And, I don't know if anybody's ever tried to see if area terms, could I interpret that as some sort of boundary condition on the wall? If you put things in a box and it depends on whether you have Dirichlet or Neumann conditions on some field in the box, and is there an area term that's sensitive? Yeah, I don't know the answer. Probably there's some idea.
If I go back to IPhT, I thought for pretty much any space there's a term in the entanglement entropy that goes like the area, but it's a divergent.
Yeah, I mean, divergent here would mean, cut off on the scale of the lattice spacing. So then we have to then we have to know, are we at a volume that's big enough so that the area divided by a small cutoff squared is less than the.
Is this something that comes up with the systems that you're considering? And also, should I think about that? I thought that maybe I should think about that as some sort of indefiniteness of the entanglement entropy in the case of IPhT.
Yeah, I think I agree with that.
In your finite quantum systems, the lattice spacing?
Yeah, so, I think of the lattice spacing, right? So I think we would get, if we say the lattice spacing is little a, right, and we're in 3 dimensions, we would get some term that's a over a squared, and then we would get some thermal term that goes like the volume times T cubed or something like that, where T is the temperature. Sorry?
There seems to be a clear separation.
Yeah, there's a clear separation. Yeah. Right. And now, so I guess to be in a thermal limit, even though this has this little a here, which we can think of as small, to be in a thermal situation, we want this to be much less than this. But yeah, I think in general, we get these contributions, both contributions.
Is there any sense in applying this idea of Jaynes to a classical system and saying that
Oh yeah, I mean, Jaynes was mostly thinking classically. Jaynes didn't much like quantum mechanics. Found it annoying.
So you can define a Jaynes-based.
Yeah. I mean, you do exactly the same thing. I mean, I because everybody here wants to do quantum mechanics, I did it quantum mechanically, and because it does translate very simply. But if you read Jaynes' original papers, it's all cast in classical language.
Questions? Okay, thank you.
Thank you.
If you want to come to lunch and you don't have the badge,
When are we meeting?
and we meet in 15 minutes just outside.
Can you ask you, because I lost some of the results, but they can value something for any pure state. And then the ground state was really needed. Why you need a certain pure
Questo spegne tutti i volumi.
Ground state gives you the area. General, a generic
Comunque Romania è una gamma del 25.
Why are